one and all present here. On behalf of ISI Bangalore students, I welcome all of you to this lecture. I have great pleasure in welcoming Professor Rituparna Sen to this platform. Professor Sen is currently an associate professor at ISI Bangalore. She ranked first in BStat course provided by ISI in 1997. She also received the Abraham Award Fellowship by Stanford University in 1998. She is currently an associate editor for Journal of Indian Statistical Association. With great honor, I welcome the professor to enlighten us on statistics.
Hello all. This is a group of 8th to 10th class, right?
Yes, ma'am.
So I'm assuming that there will be no background in statistics. So I will keep it very, very elementary. And so let me begin. And just let me find out if you have questions, how do those questions come to me? I'm new to this platform. So can I check that in the chat or will they just ask questions?
If you allow, then they can unmute yourself themselves and ask questions. Otherwise, they can put up in chat also.
Okay. Yeah, I think it is best that you just unmute yourself and ask. So do I have to do anything or is that allowed
No,
already? Okay,
no, it's allowed.
fine. So all of you, whenever you have questions, just stop me and ask because, this is better that it is conversational. Okay, so I do have some slides, so I'll start sharing them. Yeah, can you see my screen?
Yes, ma'am.
Okay. Yeah, so this is an introduction to statistics, and I am assuming that you have not even heard the name statistics, or maybe a little bit in your school. I don't know. Let us see. So we'll start with defining that it is the science of decision making in a world full of uncertainties by learning from data. So there are a lot of jargon here, and let us go through them one by one. So uncertainty, what do I mean by uncertainty? Let us start with an example because we are all worried about COVID and vaccines, and some of you, many of, maybe all of you are below 18 and even haven't received the vaccine, and maybe some of your parents have or friends have, and so on. So there is the thing that vaccine protects against serious COVID, hospitalization or death. So we might still be having some asymptomatic or mild symptoms, but if I have the vaccine, I am kind of confident that there will be no serious COVID. So in a certain world, what that would mean is that if you take the vaccine, there will be no hospitalization. And that is the kind of math we do. You do this, this implies that. However, in the real world, this is not true. What we are seeing that even after taking the vaccine, some people are having serious COVID, they need hospitalization, some are even dying. So then is there no gain in getting vaccinated? Why all this big fuss then if you can get COVID even if you are vaccinated? So that is the real world for you, that it is not really like math that take vaccine, no hospitalization, no vaccine, you can die of COVID, things like that. So, but is there still some gain? And that is what is the uncertainty, that yes, indeed, maybe, I don't know how much, but we will find out all these things gain in vaccination. So it is not really a 0-1. It is not really a black and white situation. But how do we know how much gain there is? So we have to look at the data. And that was my second jargon in the definition I provided. So in an uncertain world, we try to make decisions based on data. So what is data? Well, this is one piece of data that I found. This is the share of hospitalizations among those with COVID who are not vaccinated, that ranged from 95% to 99%. So what that means is that all those people who are hospitalized due to COVID in each of the states, you find what percentage of them are not fully vaccinated. And in the state of Alaska, it is 95%. So 95% of those who are hospitalized due to COVID are not fully vaccinated and 5% of them are fully vaccinated, and this goes up to 99.93% in New Jersey. So most of the cases that are coming in for COVID hospitalization are of people who are not vaccinated. So these numbers are really big, right? So you would, if there is no effect, then you would expect this to be 50-50, that there is equal chance of people who are vaccinated versus those of who are not vaccinated being hospitalized due to COVID. So this number actually is quite impressive, and it tells us maybe there is there's a lot of gain in being vaccinated. And similarly, these are the numbers of death. So the first one is vaccination, the second one is of death. And even here we see that mostly people who are passing away due to COVID are those who are not vaccinated. And this is the source of this data. Now, this is good, but you might still ask the question that is this because less people are in the vaccinated group? Because if there are 5% of people in the vaccinated group and 95% in the unvaccinated group, then you will see, even if there's no effect of vaccination, you will see only 5% of people in the hospitals are the vaccinated ones and 95% of the unvaccinated ones. So is that the issue? So we have to ask that question, that is this because less people are in the vaccinated group? Because if the vaccinated group is small, then hospitalizations from that group will also be small, obviously. So then I go to the next data set that I could find on this, and that is the percentage of population who are vaccinated by state. And here you see that, so this dark green is over 60%, and this light green is over 40%, 40 to 45%, and so on. So if this really yellow regions, then they are less than 40%. But most of the states, they are at least above 40%, if not above 50% vaccinated. So that is not the case, that less people who are vaccinated are being hospitalized because less people are vaccinated at all. So that is not the case. So almost half, like most of the states have at least half of their population fully vaccinated. And then comes the third part of the definition, which was taking decision. So I have talked about uncertainty, I have talked about data, and now I'm talking about the decision. So in the decision, we are given harder questions, which is like maybe now this 50% is vaccinated, but what is the date range for the hospitalization data? If it is a long range, then in the beginning, not so many were vaccinated. So I went in and I found that, and I made sure that that is not the case, and this is okay. So now comes the statistics analysis question, that is it possible that for two equal sized groups, if samples are drawn randomly, then 95% will come from one. So where do I get this 95%? This is the Alaska data. So that was the lowest percentage of people who were the non-vaccinated ratio percentage among the hospitalization. So I took the 95%, and I am asking now that maybe this is just because of chance, right? So let us say you toss a coin, the chance of getting a heads is half, but you still get the heads, right? So or sometimes you do get the tails, although this is still half. So if you do it 5 times or 6 times, it is not that exactly 3 times you will get heads or exactly 3 times you will get tails. So even if things are perfectly random, and even if the two groups are of equal size, it is still possible that you get 95% from one group. Now the statistical question is, how likely is that? Okay, is it a very unlikely event, or is it quite common? So of course it is possible, but my question is, how likely is that? And then comes the question that you have been doing mathematics, and all of you are very strong in mathematics, so that is why you are in this camp. But do you know any mathematics to do this calculation, to put a number on this likely, the word likely, how likely. And that is where we talk about the branches of mathematics, which are probability and statistics. So probability is exactly that. It says how likely things are. And then comes statistics, where you actually do the analysis on the data. A little simulation exercise, and many of you may have done a little bit of coding to know how this kind of things are done. But even if you haven't, I will explain what I am doing. So I am starting with two groups which are equally likely. So I actually just toss a coin and get a heads and tails basically. So get a 0 and 1. And the 0 would mean they're coming from the unvaccinated, the 1 would mean they're coming from the vaccinated group. And then I see and I keep counting. So it is like you keep counting. When you have a total of, say here I have this 100, when you have 100 patients in the hospital, then how many of them are coming from the unvaccinated group, or what proportion are coming from the unvaccinated group. And that is what I plot here, and I have several paths. So I do it again and again. So for each of one path here means that I am doing this calculation once. So I'm taking one toss of a coin, or one person from either of these vaccinated and unvaccinated groups with probability half, and then I'm seeing whether that person is coming from the first group or the second. And then I'm taking the second one, I'm taking the third one, I'm taking 100 of them and seeing what proportion of these 100 people are coming from the unvaccinated group. And then I'm going up to 200 and so on. I actually kept going, and the more I go, all these lines come more and more close to 0.5. That is one thing. The other thing is, these two lines above and below are for the 5% and 95%. You remember, this 95% was what was observed in Alaska, and in the other state it was, the states is what is even more. And see that none of these lines, and I did it about 20 times, go even close to this line. And you can do it many times, and you will see that it's very unlikely that one of these lines will cross this 95%. And that tells us that if indeed, so what was our assumption here? Our assumption was that it is equally likely for people who are vaccinated and those who are not to be hospitalized. And that tells us that that assumption cannot be true. Because if that is true, and if the group sizes are more or less the same, then it is very unlikely that we will see 95% from one group in our observations, in our data. Okay, so that is the first example that I wanted to show you, to introduce you to the concept of statistics and what we are really measuring in statistics. Because even if you are doing statistics in school, you will possibly start with drawing histograms, which are really necessary, which are nice, but they don't really tell you where you are going in statistics. And this is where you are going. You are trying to say that when you observe some data, what does the data want to tell you, and what does the data want to tell you about the reality, which is how likely things are and so on. So that is what the data tells us, that it is very unlikely that if the proportion of hospitalizations were same in the two groups, then it is very unlikely that you will see 95% coming from one group. So indeed we have to reject that assumption that that it is equally likely to come from each of these groups. And since you are seeing more from the unvaccinated group, therefore it is more likely for people who are unvaccinated to be hospitalized. So the whole message is, as soon as you can, go get vaccinated. So I'll take a little break here and let you ask questions on this before I go on to the next concept. Are there any doubts or questions? Okay, so let me continue then. An important aspect here is variability. So we need to do statistics only in the scenarios where you do have variability. If you are, measuring the value of G, that is your experiment, then there is very little variability, and you don't really need much statistics there. Or you are doing a chemistry experiment. Titration, how much of this it takes and how much of that it takes, things like that. Those are deterministic experiments, and you don't really need you don't really encounter much of variability there, although there will be a little bit maybe, depending on where you are and you are measuring the G and so on, but not too much. So we are talking of experiments when there is a lot of variability, like in the example that I gave you, this whether a person will get seriously sick or not with a particular disease, that really depends on a lot of factors of that person, or how much load of virus that person has been exposed to. All these things are really there's a lot of variation there, and you don't really have a formula to put it down in, or some fixed numbers there. That is the kind of situation we are talking about. And so there are a lot of experiments and processes that are not deterministic, and that is where statistical techniques are useful. They're useful for describing and understanding this variability. So what we mean by variability is that the successive observations of a system or phenomena do not produce exactly the same result every time you do it. Statistics gives us a framework for describing this variability and learning about potential sources of variability. Where is this coming from? As I said, it will depend on, in the previous example, how healthy that person is, the person's age maybe, and how much load of virus they're exposed to. So these are various sources, and they may affect the results. Okay, and how much is the contribution of each of these sources in the variability? All of those things we can study. The next concept is randomness. So when you're doing an experiment, there will be some errors, and there could be systematic errors, which are maybe you are using an inaccurate instrument or something, and those can be fixed. So those are fixed errors. If you change the instrument, that error goes away. So they can be detected and avoided by properly calibrating. Whereas on the other side, there are some random errors, which are generated by a number of unpredictable variations in a given measurement situation. And you can think of, like, when you are tossing a coin, why are you getting two results with half and half probabilities or half and half chances? If you knew all the factors, that where you are tossing the coin, how much torque you are putting into it, and how much force you are putting upwards, and how long it will take, and exactly if you could write down the equation of the coin, then you could actually say what that outcome is going to be, and you actually can say. But often it is not really worth our time to sit and do all that calculation, and more than that, often it is not even possible to do that calculation. So those kind of errors are the random errors, and those could be, as some of them could be in a mechanical situation, vibrations of instruments, because I was talking of instruments in the previous example of systematic errors. Variations in voltage, friction, humidity, all these things. So randomness really cannot be predicted. Results of an experiment which involve randomness cannot be predicted. However, there can be some order in the randomness. So even though the result of a particular toss of coin cannot be predicted, you can say that in the long run, half the times you will get the head. Okay, as I was showing in my simulation, we did not know exactly where those paths will be, but in the long run, all of those paths seem to be going towards the value 0.5. Okay, so there is some underlying order, even if individually there is randomness, and that order is something you want to capture through mathematical tools. So here is one experiment in variation. This was done by Edward Deming, a famous industrial statistician, and contributed to the Japanese quality control. And this is an experiment that shows us that we should not try to over control in a random situation, in a random experiment, in an experiment that gives random error. So over control or tampering can actually harm. So let us see this experiment and the apparatus. So what it is doing is that there is this whole apparatus, and marbles are dropped through the funnel. Okay, so you see this funnel here, and you are dropping marbles. So you expect that the marbles will drop exactly on this target. But there is, of course, maybe a little bit of wind, some measurement errors, some vibrations. So unless you can put this in a very sanitized place where there is no air and no movement and nothing, there will be a little bit of random error, and the marble will not fall exactly at the target, but maybe a little far away. And that is what we will measure, and we will try to move this whole apparatus. Our target is to make the marble fall on this dot. So what we will try to do is to move the apparatus if necessary to make that happen. The funnel was aligned with the center of the target. Marbles were dropped. The distance from the strike point to the target was measured and recorded. And the first strategy is that the funnel is not moved, nothing is changed, and you keep on repeating the process and recording where the marble is falling. The second strategy is that if the marble falls, say, to a little bit to the east, then move the whole apparatus a little bit to the west, so that in the next time you expect that that error will be corrected. So the funnel is moved equal distance in the opposite direction to compensate for the error. And again, the next marble is dropped. So in the second strategy, after dropping every marble, the funnel is moved and things are adjusted according to the previous drop, expecting that the next time the marble will actually fall on the target. What we see is this: the dark line is what happens, the distance between the target and where the marble actually falls. That distance is plotted, and in dark line is when there is no adjustment, and the light blue is when there is adjustment. So what you would expect is, if you do the adjustment, then the distance should decrease, right? Then the marble should fall closer and closer to the target, and you should get closer eventually. But apparently that is not happening. In fact, the light blue dots are even further away, often further away from the target. And that is that there is much more variation, much more variability. And what that tells us is that when there is random error, over tampering, trying to correct too much, can actually increase the variability, because there is already some variability in nature that you are unable to control, because you are not really able to control the actual factors, which are wind flow and general vibration, stuff like that. What we're controlling is something else, and that is introducing its own source of variability. So actually the variability is adding up. You are increasing the variability instead of decreasing it. So this is not something one should do. If there is random error, then that cannot be corrected, then one has to live with it, and that cannot be fixed by some other systematic, introducing another systematic error. The systematic error will only increase the variability. This is relevant not only in this case, but often say you have a lifelong disease like diabetes or hypertension and things like that. So hypertension, maybe I will give the example. If you, not you maybe, but your parents, or for me, we go to the doctor and they see that the blood pressure is elevated or less, then they will just, right then, they will not put me on medication. They will tell me to go back home, get a machine, test it for a week or so, morning, evening, so get 14 numbers, and then come back to the doctor, and then if she or he sees that there is a systematic increase in my blood pressure, only then they will put me on medication. And that is kind of the same, in the same spirit, that one or two measurements can be off. All these things like blood pressure and all our bodily measurements, they have inherent random variability, and if you try to overcorrect, then that will only cause more harm. Okay? Every time if your blood pressure is elevated, you give one medicine, and if it goes down, if you give another medicine, it will just increase the variability, just like in this picture. So that is the lesson from here, that that there is variability, and you cannot correct random variability with systematic changes. So that's a lesson, that process should not be adjusted in response to random variation, but only when a clear shift in the process becomes apparent. So you can keep observing, and if you see again and again the marble is falling in the same direction, which is away from the actual place, then maybe you can do a change. And for that, there is a very developed specific branch of statistics in quality control, which develops these ideas and tells us how to do such things. So process adjustment should be made to return the process outputs to their normal values only if so this is a control chart, is a kind of thing that is used in that is a very elementary thing, but there are a lot of other developed methods also. And you plot the values, and if it goes outside of the normal variation and keeps on doing that for a while, only then you change things. And those, how much is a while and how much, where should the limits be, all those things require a lot of calculations, and that is where the mathematics come in. So you might be wondering, why am I telling you all these stories and there is no mathematics, and you had selected here based on your mathematical skills, and each of these things actually requires a lot of mathematics to develop where those things should be, and that is where the mathematics will come in. So this is an example of where the process is actually shifted, and then you need to make a correction. So you see that it is remaining high for a long time. In the third section of my talk, I will give some real examples, real applications of, of course, everywhere people are using statistics nowadays, and even if you read a newspaper, you will see a lot of numbers being reported and so on. So I have chosen 3 examples which are close to my heart, and they're in the general idea of traffic, but someone is air, one is road, and one is internet, and I will just give a little introduction of some examples of where we are using these statistics. The first one is air traffic example, and this has been done by my colleagues in ISI Delhi. Antor, who was also my classmate in ISI, and is now in ISI Delhi, a probabilist, and Deepayon, he is working mostly on the software R and issues related to computation. So in the air traffic, the issue was that an airspace has to be safe. You don't want collisions between 2 aeroplanes. And an airspace is safe if under a nominal flying condition, which means that there is no rain or things like that, the risk of occurrence of a fatal collision between 2 aircrafts is smaller than some fixed standard. And this standard is known as the target level of safety, which is, there are 8 zeros followed by a 5 after the decimal point. That many accidents per flight hour. This means an airspace is safe when out of 2 crore flights in 1 hour, flying in that airspace in an hour's time, on the average, we will observe at most 1 fatal accident. So that is, you have to fix it at some number. If you want that probability, that chance of accident to be 0, which you would ideally want, then you cannot fly at all. You will have to fly one flight at a time. Once it has landed, then you let the other next one fly, and so on. So as long as two aeroplanes are sharing some space, then there will be a probability of collision, but you want to keep it very, very low. So one fixed number has been decided upon internationally. So what is the data? Now we have seen in the first example that if we want to do such things, we need data. So a specific monthly data, typically in the month of December of every calendar year, is used for this investigation. It is called traffic sample data. And then one also collects cumulative data on all the navigational error which may have occurred in the past 12 months. So the first one is how many flights are going, how much is the traffic, and the second one is all the navigational errors that may have occurred. And then the monitoring agencies use all these to estimate the risk of collision. So till 2011, the safety monitoring of the airspace in the Indian over the Indian subcontinent was done by agencies outside India. Indian airspace consists of three large water bodies: Bay of Bengal, Arabian Sea, Indian Ocean, and the vast region of the Indian subcontinent. For this region, this analysis was done, and since 2011, following this work, they have prescribed a distance, a horizontal separation, and a vertical separation. And so this is how much they have prescribed. The lateral separation between all parallel routes and the longitudinal separation between the front and behind of aircrafts. And this is what is being followed since 2011. And this has been recognized as a better model which decouples random lateral deviations and deviations due to navigational error. So there can be random deviations and there can be actual deviations because somebody made an error. Maybe the person who is flying, or maybe people on the ground who are directing the flight. So everybody can make some actual mistakes. So this model, it separates those two kinds of risks, and it prescribes how much should still be the separation between the routes. So this is quite interesting, I think, because it is actually being used, and it feels very powerful that as statisticians we are prescribing something that is responsible for the safety of so many people on the air. The second example is a road traffic example. Again, it is close to me because this is my sister, who is Faculty of Computer Science in IIT Delhi. And this work is a little old. It was her doctoral work when she was in IIT Bombay. And she was actually in Bangalore collecting all this data. Because she tells me that the Bangalore police were very, very helpful. So what this does is it tries to find out if a road is congested or not. And this is actually a little before all the Google Maps that we are always using. So now Google gets all the data automatically because everybody is carrying a smartphone and Google can track you. But this is before that. So what she did is put a sender and a receiver, two instruments on two sides of the road, and that sender sends a signal and the receiver receives it. And if there is a lot of traffic on the road, then a lot of that signal will get lost. So she counts how many packets of the signal are being received. And based on that, she has to infer about the traffic on the road. And this plot I will explain to you because you have probably not seen plots like this. So this is called a CDF. What that means is that on the right hand side, on the bottom there's numbers which is for the number of packets received, and then each maybe I'll start with the blue one. I think it is separated, easy to understand. So this is one line, and for example this corresponding to 10 here on the x-axis. For the blue line you see about 0.7 on the y-axis. So what that means is that that at least 10 packets were received, that probability is 0.7. Did I say correct or wrong? I think. No, less than equal to 10. So probability of getting less than 10 packets is 0.7. Okay. So at most 10 packets. And then the probability of getting at most 15 packets is a little more than 0.8 and so on. So that is what this means. And you see that these red lines are very much to the top, which means that most of the packets are being received. So for example, 15 packets have been received, the probability is quite high. Whereas here, these black lines, no, again I messed up. So you are receiving less than 15 packets, that probability is more than 0.9. So the probability that you are receiving more than 15 packets is quite low here. So for the red lines, a lot of the packets are getting lost. Whereas for the black lines, a lot of the packets are getting received. And then you go and see what are these black and red lines. Well, the black lines are the early in the evening, and then something happens around between 6:22 and 6:27, and after that very few packets are received. And that is when it is now, if you think about it, what is going on, then that is when the office time peak traffic starts. So once the peak traffic starts, less and less packets are received, and there is, which means that there is far more congestion in the road after 6:30 p.m. And this is so clear, and this is real data, and it shows us that after 6:30 p.m. on this particular junction where this particular data was collected, it gets really congested. So that is the road traffic example. And finally, I have to say something about my own work. So this is some work that I did in a summer internship that I was doing during my PhD in Bell Labs. And this is a joint work with Mark Hansen, who at that time was working in Bell Labs, but now is in Columbia University. And what this does is, I'm looking at internet traffic. So Bell Labs has an internet. Bell Labs is a web page, and that a website, and that website has a lot of pages, and people are going from one page to another. Okay, so in each page there will be a lot of links, and you will click a link, you will go to another one maybe. So that is the kind of data I am looking at. So this is a client. This is called a log file. So this is the client, CS Washington, and this is the date, and this is the time, and they are starting from this. They're starting from this particular one, the referral, which is a search site. They're first coming to the Bell Labs stat page, and then they're going to the next page, and so on. Okay, so they're navigating from one page to another, and that is so inside the stat, they start from the index, then they go to the style win dot this, and then they go to this image, and then they go to another image, and so on. So this is where how they are going from one link to another. So that is my data. And what do I want to do with this data? Well, what I want to do is, given a particular navigation pattern, we want to predict where they will want to go next. And why do I want to do this? So that the computer, it can actually prefetch that page before the visitor requests it. And so once the visitor actually clicks, it is immediate. They don't have to wait a long time. And this is 2000, 2001. So at that time, this was an important issue. Now, almost everywhere, the internet is very, very fast. But still, you know, if you are on a Wi-Fi connection in a, we're not on a Wi-Fi connection, you are somewhere on your phone data connection in a remote place, then this is still an issue, that how long it will take for a page to load. So you want to make the experience of the user smooth, and you want to prefetch it, or at least you want to check if it has been modified, and if it has, then you want to prefetch it, and so on. Why don't you want to prefetch all the links? Well, that is a lot of work, and that is using a lot of your data. So you don't want to do that. So you want to be precise. You want to fetch only those pages that the visitor is likely to go. And that is where the statistical word comes in. You want to say what is the most likely place the visitor would want to go to given their path. And of course, given a lot of other data on other users. Okay, so use all that as a learning sample. And for each new user, you want to predict their next site to visit, their next page to click. And this is some outcome. I cannot explain everything that is going on. The gray thing, I'll just tell you that the gray thing is good. Okay, given, so it says file 1 given file 1. So that means my algorithm has predicted file 1 and file 1 is the one that is being actually requested. So that is good. Whereas the black things are not so good. So there is a different prediction and something else happens, which means that what I predicted was wrong. And each of these bars is for a different algorithm. And I use what are called Markov chains of order 1 and 2, and then a mixture of those, and then a Bayes rule. And then finally, what was the actual best model was if I use only the large parts. And what that means is that for the learning, not use all the data, but use only those users who have been on the site for a reasonably long time. So those are the more reliable clients, and I should use only those that will give a better prediction for the other ones. And this is kind of a very common phenomenon in statistics, that when you are trying to learn and predict, then fitting on all the data may not be good. You might want to fit your model on based on some criteria, okay, so that it is more and more reliable and gives better what we call out of sample performance, that you're learning from a group of people and you're putting it out of sample, and there it is often better to not look at the full available sample. So here the subclass that I looked at was those people who are staying on the site for a long time, and that gave a much better result. So those were some examples. So now I will take again a little bit of break and let you ask some questions. And then I will go to the final section where I will actually do a little bit of mathematics. So any questions so far? Okay, so finally, I want to talk about inference. So when you will actually learn statistics systematically, you'll see that there are two kinds of things that we are doing as statisticians. One is just presenting the data, and that is a lot of work, and that takes a lot of effort and thinking also, because what is, you know, if you have like pages and pages of numbers, one just cannot make sense of them. So what is the best way to represent them? What is the best summary measure that tells us something? Like the graph I told you about the road traffic example, that was so informative. If I just gave you some numbers, that would not tell you any story. So if you just look at that graph, you see that after 6:30 congestion increases, and then see it very clearly. So things like that, those are what are descriptive statistics. It does not go beyond that particular road, that particular time, just represent the data you have in a way that is more meaningful, easier to understand. And the other thing that we do in statistics is called inference. And what inference does is to look at a data set and to say something more about a general about the general setup. So if using not that one plot but maybe a few of them, we want to say about traffic in general in Bangalore. Okay, so if we could use not one intersection but maybe a couple of roads, a couple of intersections, maybe even 10, 20, whatever is sufficient. So that is the other question, how much is sufficient, how much data should you collect? So if you could do that and then make a general statement, okay, and that is statistical inference. But you still don't look at everything. You still don't look at all the roles, but still want to make some statement about a bigger setup looking at a small number of data points. So this is an exercise in inference, and I'll dive directly into the example. So this is a statement according to US National Sleep Foundation that lack of sleep costs companies about $18 billion a year in lost productivity. So in recognition of this problem, many companies now make quiet rooms available for employees to take power naps during work breaks. And this is a US News and World Report in 2010. So many of the companies are making quiet rooms, and people can take a little break and take a nap there and then come back to work. And that is expected to increase the productivity. Now, a particular company is faced with the question that is the power nap option increasing productivity or not? Because if it is not, then it is not worth making all these separate rooms which are suitable for taking naps, giving employees breaks to take the nap, and all those things. So each of these things involves some cost to the company. So only if there is an increase in productivity, the company will make those investments. Of course, there is randomness here. The effect will not be same on everyone. So this is not a question that you can answer with the kind of mathematics that you know deterministically. You have to collect data, you have to do a statistical decision because the effect will not be the same on everyone. So it is costly and time consuming to collect data for every worker, and also even for the same worker this effect can change from time to time and so on. So it is not really possible to do a whole mapping of what will and what will not work on for which worker and so on. Things can change in future and so on. So that is why you need statistical inference. You want to look at a subset of workers for a subset of time, because if you keep on doing this infinitely, then when does the experiment end and when do you actually put in those measures of like taking naps and so on. So sometime you have to end this. So a fraction of time, a fraction of employees, you take them, you do the experiment, and then you want to make a statement about the rest. And that is why this is inference. So consider a major airline that encourages reservation agents to nap during their breaks. So there are a lot of agents who are taking reservation calls, making reservations on the flights, and they are encouraged to take naps during their breaks. And you want to make sure that you want to find out whether the napping thing is actually helping. So a sample of 10 agents are chosen, and the data is the number of complaints received about each agent. And this data is collected in two parts. One is during the 6 months before NAP was encouraged, and the other is during the 6 months after the policy change. So at some point there was a policy change, let us say January 1st, 2021. Then for the previous 6 months, how many complaints were received against a particular agent, that number is collected. And for the next 6 months, how many complaints were received about the same agent, data was collected, that number. And this was done for 10 agents. So we have 20 numbers. An increase in productivity would mean a decrease in the number of complaints. So that is what you are trying to see, that whether for these 10 agents in those 20 numbers, do you see a decrease overall in the number of complaints. So this is the data set. It is plotted. The black dots on the y-axis are the number of complaints. On the x-axis, this is the this is the identity of the agent. So which agent you are looking at. So there are 10 agents. For each agent, you have 2 dots. One is a black dot, which is before the number of complaints in the 6 months prior to the introduction of the napping policy, and the red dot is the number of complaints about the same agent 6 months for the 6-month period after the policy was introduced. So for example, this is the third agent. Before it was 16 and after it is 6. So there has been definitely 6 or 7, I'm not sure, somewhere there. So there has definitely been a decrease for this particular agent. And for most agents, you see there a decrease, but not for all. For the 6th and the 7th ones, there is actually an increase in the number of complaints, okay, which means that for these two, the policy actually did not really help and did harm, apparently. So how do you put all these 20 numbers into one measure of really a yes-no answer? Is the policy helping or not? Is the policy helping in reducing the number of complaints? Well, you can take the total, the average, equivalently any of those. So in all, there were 76 complaints for all these 10 agents for the 6 months before the policy change and 37 afterwards. So there has been quite a lot of decrease, 39 decrease. Okay, so about half. So overall, the number of complaints has halved during this period, from the before to after. So you are inclined to say, yes, this is making a difference. But you still want to have some measure, some quantification, some numbers to put there. How much is the difference? This is half for this particular subset, but is it really half? So that is what we are trying to do. We're trying to quantify this. So we have seen one particular outcome of productivity measures. Now suppose, so this is my assumption here, suppose there is no decrease in the complaints due to the policy. Okay. So if that is true, then if we interchange the numbers for one particular worker, then this could be another equally likely outcome. So we have seen this particular outcome, and if my assumption is that
we are taking at random, we are taking 10 agents, yes, but it might not be applicable for the other 10 agents. So how can we just tell that it is the average?
No, it is the average of only these people. So this 76 is actually the number for only these people, and the 37 for the same people after the change. So I'm not going outside yet. Yeah. So right now I'm talking of only these people. So I'll continue. So what I'm doing here is I'm assuming that there is no change. Okay, and if there is no change, then if I interchange this black and red, their color, then that could be just another outcome, right? If things are happening randomly, if this is just a random observation, and it is just for some other causes that there were more errors before and less after and so on, maybe because that person was more disturbed before for some reason and so on. So in that case, it has got nothing to do with the policy. Then I might as well just interchange this red and black dots, and that would be another outcome of the same experiment. So this is very crucial that you understand what I'm trying to do here and agree with me here. Okay, so again, I will repeat it, therefore, that if the policy did not matter, if the policy change did not matter, if the napping did not make a difference in the number of complaints, then if I exchange the red and black dot for a particular person, I cannot do this across persons because each person has their own level of efficiency. But if I change this for the same person, then if the policy is the only thing that is different here, and if my assumption is the policy does not make a difference, then that could be just another outcome for that same person. And that is how we proceed. And this is true for every worker as well as any subset of workers. So for example, in this picture, I have the same numbers, but I have interchanged the productivity for workers 1, 2, 3, and 5. Okay, so if you look at these two pictures side by side, you will see that the black and red colors have been interchanged for these particular workers and not for the rest. And my claim is that if there is no difference in productivity due to napping, then this might as well have been another outcome of this experiment. And it would be another equally likely outcome. Okay, so because all I have done is interchange the number of errors done in one 6-month period with another 6-month period. And if there is no difference due to napping, then these two 6-month periods are identical as far as the productivity of a worker is concerned. So this is how I get a lot of possible outcomes of the same experiment. And how many possible, and for this outcome, the decrease is 1. So I will actually get 2 to the power 10 possible outcomes, because for each worker, I can decide whether to interchange or not. So there are 2 possibilities and there are 10 workers. So 2 to the power 10 total outcomes are possible. And for each of these 2 to the power 10, I will get a graph like this, and I will get these numbers before and after. And I can look at that difference. Okay, how much change is happening between the before and after for each of these outcomes. And now if the actual observed difference, which was 39, is too large compared to the other equally likely outcomes, then we will suspect the assumption. Because if the assumption were true, then this will be a typical difference, right, among all these 1024. But if it is not a typical difference, if this is too large compared to all the other outcomes, then we will say, well, in the real data, something fishy is going on. It is not true that this is one realization, one equally likely realization from all these 1024. And then we will say, well, what could be different? Well, our assumption could be wrong, and then these outcomes are not all equally likely. Okay, and that is how we proceed. So in that case, we will conclude that there is indeed a decrease in the complaints due to the policy. And this is the exercise that I ran, and I am giving you what is called a histogram. So what that means is that between 0, 10, 20, so between 0 and 10, there are about a little more than 200 observations. So out of these 1024, and I'm looking at the difference in productivity before and after. So the number that was 1 here, it will be one of them. And for each of these 1024, I will get a number. And for those numbers, I am drawing what is called a histogram. And so that means that there are about 200 between 0 to 10, about 200 between minus 10 and 0, and about 150 between 10 and 20. And our observation, which was 39, that is way to the right. And there are only 8 of the 1024 that have a higher decrease. Okay, so from here we can conclude that the number that we have observed is very unlikely if the assumption were true, because if the assumption were true, all these cases would be equally likely, and therefore the case that we observe should be somewhere close to the middle of this histogram. But it is not. It is towards the very end, right end, which means it is a very large number compared to the other outcomes, which means that all of these are not actually equally likely. Definitely this one is not one of several possible outcomes that can be generated by interchanging the before and after times. So it is not okay to interchange the before and after times. Interchanging the before and after times before and after complaints does not keep the symmetry. Okay, so there is something asymmetric that is going on, and assumption is not true, and we conclude that there is indeed a decrease in the number of complaints due to the policy. And this 8 out of 10 gives us the quantification that we are looking for. It tells us that if indeed there was no change, then the chance of observing this number 39 is 8 out of 1024. It is very low. The chance of observing this particular outcome is very low if indeed there was no change in the number of complaints before and after the policy. So we can now quantify how large that, we had got something like 39 out of 76. So how large is that? So this is how large it is. This is the chance of getting it. And somebody may think that this is not really that small. They might still say there is no effect. That is subjective. But we have put one number that everybody has to agree to, that under the assumptions of no change, the chance of getting this observation is 8 out of 1024. Okay, so thank you. That was all I wanted to talk about, and I don't know if we have extra time, but I am free. I can talk if you want to ask questions.
Thank you, ma'am. If anyone has question, they can unmute themselves and ask.
Okay, so I did also share my email. So if you don't have questions right now, you can always email me. Not only questions about the talk, but anything. If you have any questions about statistics, or later in your career you want to follow statistics, anything like that, feel free to email me. Okay, bye.
Okay, since there are no further questions, I think we can end the session here. Thank you very much, ma'am. That was a nice introduction. Thank you, one and all.